Hey, everybody. Heather, I haven't seen you in forever. I get to talk about politics today. Somebody posted, I forget, I think it might have been Washington Post or the Times, one of them. Likelihood to vote for Trump, likelihood to vote for Biden, their numbers and their margin of error. So I'm going to show you what that looks like in a graph. And I think it will help make things a lot more clear with a real example like that. Also, I get to dump on Trump, which is always my goal in life. But this is just sheer numbers, so I'm not attempting to persuade. Okay, this is going back to margin of error, but it's also the bridge into, once again, why we're doing what we're doing with the Sprocket Company question coming up. And so my goal today is to just revisit this topic of how confidence intervals fits into what we're doing in the long run. And that will also be helping you to understand what we're trying to do with the t-test. And then I'm going to have a few, as many as we have time for, examples of one sample t-test. And then Friday will be your asynchronous Friday quiz on one sample t-tests. I'll make sure that there's some practice ones up there with answers so that you can do that first if you need to. Also, if the majority of you fail this next quiz, I will give you some more time to learn it and another example. And by talking about that, you might see what you're doing wrong. And I will let some, if we need to, I'll let you all have that quiz go over again. But don't forget, we're dropping the lowest quiz grade. However, for most of you, that is most decidedly going to be the Z-score one. Okay, hang on while I set up, share my screen. I'll be right back. I have to go grab my pencil. It's charging in the next room. Sorry about that. Gertie, we have to get that. We have to get charging my pencil. She's not settling in there. How about I leave the door open, and if you're going to make noise, can you handle that? Yeah. I won't make too much noise for you? No. Okay. Okay. I'm back. We're going to come back to this page with the sprocket problem so that I can talk to you about politics. So here's the thing. Somewhere in either the Post or the Times, I saw the article that was looking at the most recent, I guess it was New York Times and Siena College polls. I don't know if you know Siena College is a good college nearby. And I think they're somewhere just not too far from Philly. And they are nationally famous for doing really accurate polling on a number of things over the years. And they always do political polls. And they're usually one of the first ones that gets reported when people are reporting a group of polls because they're usually more right than many others. So here's what they said. They said, the question was, who are you more likely to vote for? Trump or Biden? And they gave the two answers and the margin of error. So we can use this. And I think that a picture type description of this will actually be really helpful. So I'm going to share my screen. Takes a while for the iPad to talk to the, there we go. Okay, fresh white page. So here's what we got. We got 43% said that they were going to vote for Trump. 51% said that they were going to vote for Biden. And there's a 3.4% margin of error. Let's call it 3.5%, okay, for making the graph a little bit more easily and less fussy. Okay, so this is frequency, the numbers of people who said the answer. And these are, how likely are you to vote, I guess. But actually, it's just, let's assume that there are means of, with a normal curve around them. We don't even need them to be means, but I want to use that to move along to the next topic. So let's do it. How likely are you to vote for the person that you're going to vote for? Okay, so this will be likeliness, Trump versus Biden. And I'm going to give them each a different color because that's what's going to help us. So hang on. I'm going to do Trump first in red, which is appropriate because, so Trump versus Biden. Oh, I'm being so patriotic with my colors. Okay. So Trump's was, why did this thing switch to, you can still see that screen with the white thing in the graph, right? I can't. Wow. How'd this happen? Hang on, I got to find it again. There. Okay. So first I'm going to draw Trump. So the, actually I have to put some numbers up here. Well, let me change the color. I'm blind. I can make a color though. I really need to get, okay, fine. I'm going to have to use pink. You know what? Hang on, I've got to restart share my screen. Something's wrong with my pencil. It won't talk to my screen. So I'm going to stop sharing. I'm going to zoom in and I'm going to turn this app on and off. Yeah, better. It's fixed. Okay. Share my screen. Sorry for the delay, you guys. Here, I thought I was getting good at this part. Okay. We need to put up the numbers along the horizontal axis that gives us 43 and 51 with about 3.5 in each direction. So that means we need to go down to from like 39 and up to 54. Does that make sense? We need to get a margin of error around the numbers, and I will show you what I mean. So here we have the 43, 42, 41, 40, that's 3 below. 39 is 4 below, and we need to go up to 44, 45, 46, 47. We can get Trump all in there. Okay, so 43 is the mean. The curve doesn't really help. Just think 43%. The curve's going to come in later. We're going to care about the curve in the next part of this. Okay, so basically what we're looking at for 95% of Trump's voters, his curve looks something like that. It was a bad line, actually. It's not a good normal curve. It's just the idea, okay? These folks out here and these folks out here, I'm going to erase the last part of that, are a total, the two end areas are a total of only 5%. because 95% confidence interval is from here to here. I'm so sorry. Yep, here to here. Okay, so 95% of Trump's voters are in there. Now we got Biden, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55. That's good enough. Okay. So here's Biden. There's 51, 2. That's his curve. Don't worry about the heights of them. That's just bad drawing. And basically what we've got is this, his little area here and his little area in here. Okay. Though that's 95% contained between these two lines. 95%. Okay. Notice that these two curves hardly touch each other. Right? There's like maybe a 1 percentage point overlap between Trump's voters, which I was going to do in red. So hang on and I'll highlight the redness of it. And Biden's. They look like two very different groups of people, don't they? There's not a lot of overlap to care about, which would be this group right in here. That would be our undecided folks. Notice that there aren't very many of them here. If we accept that Siena College and the New York Times numbers of 43% versus, this is 43, this is 51, and the margin of error, which is the 95% confidence interval, equals plus and minus 3.4 points from those means. There's hardly any overlap. Can you see it? Somebody make something lively. Okay, good. Okay, so we can be pretty sure that these numbers indicate that there's a strong, we're 95% sure that there is a preference for Biden at the moment. Anything could change. Trump came from behind last time gigantically, as he would say, in 2 weeks. It was ridiculously strong finish for him. We don't have the same circumstances now. He's an incumbent, but anything can happen. But right now, we have 43 and 51 with a margin error of 3.4, which means those groups hardly overlap at all. Now, imagine, I'm going to draw one in a whole new color, green. Imagine that the means were closer together. So I'm not going to be as precise with the numbers, but let's say I have the same margin of error and the means are closer together. And I have Trump's here, say, and Biden is more like here, say, same margin of error, but the means are closer together. Look at all the overlap. Look at that. How sure are you that there's a preference for Biden over Trump now? That green area compared to that pink area is a very different picture. There's much more overlap. In fact, you could actually, even if you wanted to, you could imagine that this is really just one big curve. See the orange? It's hardly two separate groups, considering the difference between the means versus the margin of error. Margin of error is telling us about the variability in a group. If I have a rather large margin of error and the means are pretty close together, I'm going to see overlap between the groups, which means they may not be two distinctly different groups. But if my means are relatively far apart compared to the margin of error, they look very much like two distinct groups. So just so you know, this one's the reality today. It's a bad picture, but if you saw a real picture, it would look like that, but drawn by a professional. And this is just a different scenario. If they were a lot closer together and they had a larger margin of error, you see that. So now I'm going to get even more abstract and not talk about anything that's really happening in the world today, and just say, okay, the blue doesn't signify anything here. It's just that it happened to be easy to grab. Here's what a t-test is trying to do. Any kind of a t-test is comparing two means. Okay, so let's say that our sprockets, normal sprocket size is here. They can vary whatever that standard deviation was, just that far apart. These out here in this tail would be unacceptable, and these out here in this tail would be unacceptable. And if I turned on my sprocket making machine and came up with the exact same curve, perfect, that's wonderful. I'm going to make good money on selling these sprockets. Elijah, were you going to ask something or say something?
No.
No, he's lit up and not muted, so that's what I thought. It's fine not to be muted, but I thought you were about to say something. Okay, but if my sprockets are slightly too big, let's go with the orange picture here. Slightly too big could make my sprocket group score like right around there. Those two means are not that far apart. Notice all of this overlap. Any sprockets in this size range, any sprockets over in here would be acceptable sprockets. But if instead I had this, here's my sprocket size, here's the number of sprockets that come in at the various sizes, and if instead, here's the population again, here's what the sprocket company wants, I mean the whatever we're making sprockets for wants, here's their unacceptable area. If my sprockets instead from my new machine were actually over here, means really far apart compared to how spread out the scores are, then this machine needs to be fine-tuned, right? I'm going to make a batch of sprockets that I can't sell, so I have to fix the machine. That's what we're in the process of trying to figure out with that problem. There's another way to look at this too that's going to make it even more obvious. Let's say that this is IQ score over here. And let's say this is the frequency of people who have the various IQ scores. I'm going to do this is going to be what the independent t-test pictures look like. I'm going to put men and women. Okay, so we've got here's men's IQ. Here's women's IQ. That's pretty accurately drawn, to be honest. Okay, so this is 100 right in here is 100. Okay, notice that the means are really close together and that the curves are really spread out. When the means are close together, but the variability within groups is big, we usually find that there is no statistically significant difference between those groups. But if instead I take something instead of IQ for gender, we can do IQ for say the kids in a class that's set for kids with developmental disabilities versus the kids in the gifted and special, whatever they call that class. Those two curves are not going to look like these really close together. They're going to look more like this. No touching them at all. They're very different groups of IQs. Is this making sense? Isaac's like, I hate this, I hate this, I hate this, I hate this. So what we're always looking for is to compare the difference in the two groups' means relative to how spread out they are, because this is very different from this. Okay, so in the end, all of our stats with t-test is going to be something about mean differences divided by something about variance or standard deviation. It's a comparison of how different their means are relative to how spread out they are. That's what t-tests are trying to do. So now I'm going to take us back to the problem that we were working on. Sprockets. I find the politics one much more interesting and compelling, but we're going to work on sprockets first. I think that that's the most extreme difference that I've seen so far on the who's voting for whom and how spread out the scores are. That's clearly the most distinctly different groups we've seen so far. So it looks like the closer we're getting to election day, the more sure people are about who they want to vote for, which makes sense. Okay, so here's what we got so far in the sprocket thing. In case you weren't paying attention last time or you weren't here, we have a brand new sprocket company and we got a contract from some company to make them sprockets. They want the sprockets to be 6.3 millimeters across because they've been having sprockets from another company. They know what size they need, 6.3 millimeters across with a standard deviation in any group of sprockets we make of, oh, we don't even know. We don't know. We don't care. But we are going to try our new sprocket making machine out to see if we're up to snuff, to see if our sprockets are close enough to what their standard sprockets are, their population. So because it's titanium and expensive, we're just going to run 10 sprockets through the machine and measure them. And then we're going to do a one sample t-test to determine whether the sample of 10 sprockets is close enough or is it significantly different from the population of sprockets with their 6.3 millimeters across thing. So if our t-test tells us that there's a significant difference between our sprockets and the population sprockets, we're going to have to fine tune the machine. But if it says there's no significant difference, then we don't have to fine tune the machine. We can just keep running them and send them. Okay, so how we test this is we set alpha first. How sure do we want to be that we're correct? Well, this is just our first run ever. But we do want to be pretty damn sure because we want to be able to sell these sprockets. So we're going to go with 95% sure we're correct. And we make sure that we have the population mean. And then we make hypotheses. We say that our sprockets are going to have the mean that's the same. Our sprockets mean will be 6.3 millimeters. But it's not going to have to be exactly 6.3. We just need to be 95% sure. So our sprockets are going to be in that confidence interval, that 95% confidence interval. These pictures that I've been drawing with the lines going around them. See these dark, black, ugly lines on the edges of the curves? Within them is our 95% thing. Okay, so we want to be 95% sure. So that's why we said alpha first. And then we say our sprockets are going to be just about 6.3 millimeters. The alternate hypothesis, which in this case we do not like, but we need to set one. Often we want things to work out that way, like when we have a control group and an experimental group, but this time we want them to be the same. What we want is not relative. We need to set the hypotheses up so we can test them. It's not about what we prefer. So our alternate hypothesis is that our sprockets won't be the same size. They might be bigger, they might be smaller. We don't know, first time running the machine. So we call this a two-tailed alternate hypothesis. They could be larger than 6.3 or they could be smaller than 6.3. We just don't know which way our machine's working yet. Okay, so now we're at the stage where we're going to run the t-test. Okay, we're going to actually do the math of the t-test. So the formula is this. It is the sample mean minus the population mean divided by the standard error for the sample, standard deviation over the square root of n. Okay, so we run our sprocket machine, we measure our 10 sprockets. And we get a mean from them of, hold on. So the mean, oh goodness. The mean for our sample is, I just saw it, 6.41 millimeters. And their standard deviation is 0.12 millimeters. You know how to get that information. It's the same way we always get information from a group of scores. We get the mean and we get the standard deviation, usually by putting them into a computer or calculator and getting the summary statistics, mean and standard deviation. And oh, and n, just so we remind ourselves, equals 10. Okay, so now I'm going to plug these numbers into the t-computed formula. We call it t-comp for t-computed, meaning we compute it. So it's 6.41, our mean, minus the population mean of the sprockets that already exist out there, which is 6.3. And in the denominator, we put 0.12 over the square root of 10. This is the kind of formula where things start to go south for folks who aren't used to doing math. This is not a difficult formula. It's the easiest formula that we'll have going forward. But what some folks do is they get the square root of 10 and they forget that it's only part of the denominator. You forget to do some of the steps. So you might be better off, if that's you, when that happens to you, and if it happened to you in algebra class a lot, of actually doing what I'm going to do here, which is to change the numbers bit by bit as I go through the problem. Always comparing to make sure the formula looks like the one above, but some numbers have now been put in. So the only thing that we have to do is we already have all the numbers. We just need to get a square root and do some fractions and a subtraction. So I'm just going to work the steps here. I don't even know if I have them actually. We might have to do. Now I got it. Okay, so the numerator turns out to be 0.11 divided by, oh man, the example I used was 25 and not 10. Well, we're going to have to do it together. Divided by 0.12 over, what's the square root of 10, somebody?
3.16.
3.16? Anybody else? Hi, Elijah. Yeah, I'm seeing yeses. Okay. And that equals 0.11 over, what do you get when you take 0.12 and divide 3.16?
I got 0.04.
You guys back in a room together again? I can hear that. Isaac, tell Sam your answer.
0.04.
0.04. Anybody else? I need confirmation.
You said 0.12 divided by,
Yeah, 0.12 divided by 3.16, Elijah. Come on, folks, get this simple math done so we can move on, so you can have examples.
I got 0.04.
0.04 twice now, I'll take it. So finally, the last step, 0.11 divided by 0.04, what do you get?
I got 2.75.
Yeah, me too. So T comp equals 2.75. Okay, what do we do with that number? What does it mean? Just think of it as an indicator number. Just think of it as an index, T like Z. It's like the Z number doesn't have anything to do with what the numbers actually are from data. Like you could be looking at data where the scores range from 1,000 to 12,000, and you can end up with a Z score of plus 1.6, right? So the Z doesn't really tie in with the data numbers. T's the same. T's looking at how far apart the sample is from the population kind of stuff. Okay, so we've got T computed. We need to compare this T to a T critical value. And what I mean by T critical is, I'm just going to draw a little bit right here. What I mean by T critical is, here's a curve, right? Here's our 95% point. We got 95% of the curve is in the middle between those 2 points, whatever those scores are. And to work with it, we're going to need to get the T scores that go there and there. Okay, so to do that, we need a T table, just like we needed a Z table. I put one up on Canvas. This T table is more complicated. You're going to want to follow it on your own screen. I'm going to figure out how to pull it up. I think I forgot to stick it on my, it's on another app, just hang in there. I'm going to stop sharing for a minute while I go hunting. Oh, beautiful. Okay. Sharing again. Okay, so can you see the table? I'm screen sharing. You can't see this
No,
with
it's
the
just,
blue lines?
no,
Really? Try this. Strange. Now can you see it?
no.
Why?
We see, what you just did, the equation you just did, maybe it's
But
still
you don't
showing
see a
that.
big typed in T table.
No.
Okay, you're gonna have to go on Canvas. I put it into a module. It's odd. It's telling me that my shared window is not on the top, but that's exactly what was on the top. So strange. Does everybody who want to see it, can you see it? It's got blue areas and white areas. Tell me if you actually are looking at it, anybody. I need to know whether, I don't want to proceed unless you can see it. Or I should say until you can see it. Elijah, are you looking at the table?
No, it won't load on my my iPad.
From,
What one is it?
hold on, I'm
There's-
gonna go looking.
2 on here, I think.
Oh, it's,
There's table, the normer, what one are we looking, the last one is just the T table.
up to 100 or something, I think I called it. You can see things if I put them, if I'm on the web though. So perhaps I can do T-table. And call it up from the web. It's pretty funny. These folks wanted it available to everybody. So just go to ttable.org. That's where I'm finding it. I'll put it in chat. This is a table I'm looking at. And I put it, I put it up in Canvas, but just go here now because it'll go faster. Now, can you see it? Oh, no.
Yeah.
For yourself, you can see it on your own screen?
Yeah.
Okay, that's better then. Thanks. All right. So we need to find what we call T critical. That's what we call this. This is critical levels of T. In other words, it's the levels that define the inner whatever percent we are looking for. And in this case, we're looking for 95% because we said alpha to be 0.05. So this is step 5, T critical. There are more things to have to know before we can get this. Before, we just needed to find across the top the 0.05 and going down degrees of freedom. But now we have to choose between one tail or 2 tails to be able to find our 0.05. Can you see that? Going across the top, the bold. There's 0.05 twice. 0.05 in the top row of those 0.0 whatevers is about halfway in. And 0.05 on the bottom row is 1 off to the right. Ignore that cum prob row. Just 1 tail, 2 tails is what we need. So we're looking for knowing how many tails. So 1 or 2 tails. I'll give you a big hint. We already decided. The way that you know whether or not you're 1 or 2 tailed is what you were thinking when you made your alternate hypothesis. So you made your alternate hypothesis. In this case, remember, we're trying to match the sprockets. If they're too big, we reject them. If they're too small, we reject them. Both tails, all the sprockets all the way out on the edges of measurements are not okay. So we need to look at both directions. There are some times when we only care about one of the tails, and I'll make sure we do an example, but most often we care about 2 of them. All right, so we need to look at 2-tailed. Two-tailed, and we need to know what our alpha is, which we already set at the very first step. Look up at number 1, alpha equals 0.05. And now we need to know degrees of freedom. So we know how far down the table to go. Degrees of freedom for a group when we know some things about the data as in n and the mean, which we know 10 and 6.41. That's going to be n minus 1. So degrees of freedom equals n minus 1 equals, in this case, 9. 10 minus 1, because we had 10 in our sample. Okay, so you go across the two-tailed row till you see 0.05. This is one of those, this is possibly the most important time to be in a room with you, by the way. So this is my first time trying to do this online. Just, you're going to have to put in the effort, or else 2 days from now, you're going to go, I have no idea how to use that table. So you go across the two-tailed row, which is the bottom of the top area, until you find 0.05. And then you go down until you find degrees of freedom, which is that left-hand column for 9. Now, somebody tell us what the T critical is.
2.262.
You're good, man. You're good. Who wants that explained again? Maybe by Jordan, by Elijah this time.
So once you've determined whether you're looking for one tail or two tails, you across the top set of numbers, you look for 0.05
Mhm.
in the two tail row, and then you go down to 9, which is your degree of freedom, and then you just follow the over until you reach the 0.05 column.
Yeah, that's exactly it. If anybody wants more help with that, we should have an appointment where I can figure out finally how to share this with you, or you can actually get it up in front of you and we'll talk. You can share your screen. Okay, so we have now got T computed and T critical. I'm going to highlight T critical here. And now we move into a decision. Step 6. This next step is to make a decision and write a sentence a 6th grader can understand. Truly, that's what this step is. Make a decision and write a sentence about it that a 6th grader could understand. There's going to be a certain format to this that built into the statement that's a little bit fussy. Okay, so here's how we make a decision. If T computed is greater than T critical, then we reject the null hypothesis. The null hypothesis said ours will not be significantly different from the population of sprockets with their 6.3 millimeter size. So, and say there is a significant difference between the sample mean and the population mean. Population, sorry for the extra letters there. Mean, which is mu. However, if T comp is less than T crit, then retain the null hypothesis. You can't see what I'm writing. What the hell? I forgot. You guys need to yell at me a lot more often. Share screen. Sorry. Just remember that you couldn't see it. I'm doing really fine with the math today, but it's the sharing of stuff is killing me. I'm just going to probably leave it on share my screen for the next 3 weeks. Yeah, I've been carefully writing it out for you. Sorry about that. So if T-comp is greater than T-crit, we reject the null hypothesis, and we say there is a significant difference between the sample mean and the population mean. And if T-computed is less than T-crit, then we retain the null hypothesis and say that there's no significant difference between the population mean and the sample mean. I wrote that backwards, I know. Between the sample mean and the population mean is what I wrote. It's the same. So that's how we make the decision. So we call this the decision. And then we're going to make a final statement.
So it doesn't matter how much more than T
No,
critical.
think of it, it's a yes/no decision. It's
Okay,
an
so
on-off switch.
1 point
0.01,
something,
0.01.
then it's okay.
Yeah, if it's more
Thank
than,
you.
and they will never be exactly the same. They won't.
Okay,
If it ever happens in real life, do me a favor and email me at dmaluso@gmail.com, because eventually I'll retire, and tell me, you won't believe this, but I just did a study for work with 1,000 people in my sample. It came out exactly the same as the population. I'd love to know. I've never heard of it, ever. Somebody actually wrote an academic paper about it, just to get people who had experienced it to mail him, because this was back in the old days, mail him their results, because he was convinced they had done the math wrong if they ever found them to be exactly the same. He's a funny guy, yeah. Okay, so we make our decision. So in this case, T computed is 2.75. That's the green stuff. T critical is 2.262. So which is greater? Oh, come on, somebody just use your mic.
T computed.
Thank you. Check. Good morning. Or now, good
Morning.
afternoon. Okay, so T computed is greater than T crit in our case. So that's this first part of the decision. If T computed is greater than T crit, that's us. 2.75 is greater than 2.262. We're going to reject the null hypothesis. So we're going to say there is a significant difference between the sample mean and the population mean. And here's how we write that. We say reject the null hypothesis. The sample sprockets with their mean, oh, sorry, that's an X bar, is, was it 6.41 or something? Yeah. Are significantly larger, bigger, whichever word you want, than population sprockets. With their mean of 6.3. And then we have to include in the sentence, I'm going to put this down below, but it's all part of the same sentence. We write this when we do a t-test. T with, in this case, 9 degrees of freedom, that we just put a subscript 9 in parentheses, equals whatever T computed is. So 2.75, I think we got, right? Yeah. And this next part is difficult to understand why I'm going to do this. Watch. P is less than 0.05. Okay, so what that means is our T computed
It
had
down.
9
I can't see the bottom of it. Or move it up. Oh,
Oh, the whole screen up, I remember now.
thank you.
I'm trying. It's not moving. Hey, can you see it now? I can't hear you, Heather. Can you see it?
I don't see it. I don't. Maybe it's just mine.
Okay, new page. Oh, I'll just put it over here off to the right. The whole sentence you could see, but not the last part. Okay, before we put a period at the end of the sentence, we say T with 9 degrees of freedom equals whatever you got for T computed. 2.75, comma, we say P is less than 0.05. Here's what this means. Our T with 9 degrees of freedom, which tells us there were 10 people in the 10 sprockets in the sample, is 2.75. And that probability that I'm wrong here is less than 5%. That is a fancy way to talk about margins of error. But what it's doing in addition is it's saying those means are too far apart compared to the margins of error, compared to the variance, the variability, the confidence interval. The means are too far apart. There's not enough overlap between the population sprockets and these sprockets. So what would I then do if I was managing this company? What would happen next? Isaac, do you know?
He says change the machine.
Yeah, change the machine. I knew you'd know. Change the machine, adjust the machine to make somewhat smaller sprockets because ours were 6.41 and the populations are 6.3. So we try again. We make 10 more in a smaller setting and see if we got close enough, right? This is probably pre-digital because now I'm pretty sure that you would be able to type in exactly what you wanted those sprockets to be with digitally controlled machines, but you just have to imagine that it's not. Now, hold on one second. I just want to see. No, I was checking to see what happened in the example I used of this, where I did the same exact numbers, but I ran 25 of them in this version of solving it. And even then, even with more in the sample, we found out that there was, that the sprockets are still too big. Now, look at the table again. Look at the T table again. And I'm guessing you can't see it on my screen. Yeah, interesting. How strange. Okay. Imagine that we did the exact same thing, got the exact same mean, but instead we had 25 of them. So look for degrees of freedom as 24. And you find T critical for the same problem, 0.05 two-tailed.
$2.064.
2.064, which is actually easier to find a significant difference because that's a lower number than what we had in our version, which was 2.262. So that T computed doesn't even have to be as large. What we end up getting when we have more is that we end up getting a T computed of 4.58. That's the power of having more people in the study. Your T values go up and your T critical values go down. It's easier to find a significant difference if you have more people more sprockets in your study. Okay, we're going to do another one of these problems. Okay, I got to get to a clean page. Hang on. It's going to take a little while. Wow. I think I found it. All right. You could see the plain white page and you could see this.
Yeah.
You could see drawing. Okay, just checking because things have changed. All right. In this case, I'm talking about a researcher who, sorry, I'm looking off to the side where my old handwritten notes are for problems because they're good problems. So trying to figure out the nutritional needs of the rats kept in an animal lab for studying behavior. Their nutritional needs, the researcher felt like maybe they weren't being fed the right stuff. And he was specifically concerned about copper levels. They were showing symptoms of low copper. And so he decides, since he's a behaviorist and likes to study rats, boo to him, by the way, that he's going to test rats that he raises with a copper deficient diet compared with what he already knows about rats that are not deficient, to see if the rats in his lab are not getting enough copper. So he's going to give him his version of the rat chow that he's worried about versus Purina rat chow, which is famous for having the right amount of copper. And in case you don't believe me, there actually is such a thing as Purina rat chow. You should look on their website. It's really kind of weird. They have Purina rat chow, Purina, name the animal, they have the chow, for real. Like frog chow, probably, snake chow, I don't know. They've got all these different animals. There's llama chow. There was a couple of years ago, I found llama chow. So rat chow doesn't seem so very special anymore at all after you hear that. Okay, so here's what we know. We know that the population of rats in labs around the United States, that's our population, have already been found to have a certain number of errors they make when running through a maze. It's a very big maze. It gives them a chance to make a bunch of errors. And to learn the maze, it takes the average rat, the population of rat, takes them, this is just the data that we have before we start. Their mean amount of time that they take, mean amount of errors to learn the maze is 28. Now, we have a hypothesis that our rats are getting a different diet. It might make them do it in fewer errors, and it might make them do it in more errors. We're just not sure yet. So let's set ourselves up for a two-tailed hypothesis, which I'll get to in a second. So first thing we have to do, step one, set alpha. We're going to go with 0.01 because I could be basically killing rats if I get this wrong. He wants to go to 0.01. He's pretty sure he's right that there's something wrong here. Okay, next step, null hypothesis. Null hypothesis is, anybody want to try it? Sam, you think you know?
I don't think so.
No?
No. Sorry.
Heather?
I'm with Sam.
Okay. The null hypothesis is a hypothesis of no difference. It's always the hypothesis. Think about it like this. It's always the hypothesis of nothing is going on. Okay? Nothing's going on. So in other words, The rats in his lab getting fed his special blend are also going to take an average of 28 errors to learn. So the null hypothesis is that there's no difference in the number of errors made by the pop and the sample and his sample. Another way to look at that would be to say his sample's mean is going to be about 28. Questions about the null hypothesis? It's always the hypothesis that nothing's different, nothing's going on. Doesn't have to be exact. We just have to be 95% sure that we're close. Okay, the null hypothesis is followed by the alternate hypothesis. In this case, the alternate hypothesis is that remember, he's not quite sure whether this diet. You trying to wave me down here, Sam, or
Well, actually, Isaac's trying to wave you down.
what?
So for the null hypothesis to work, and if alpha is set, in this case, 0.01, if it's within 0.01, the null hypothesis is good to go. Correct?
Within 0.01, you mean the two means?
Yeah.
No. 0.01 just tells us, it's basically saying we're looking for the 99% confidence interval, that the spread in the t-scores is going to be the 95% difference. So it tells us essentially where to look in the t critical table.
Oh, so the null hypothesis is only okay if it is 100% the
95%.
same, 95% the same.
In this case, I said it wrong. That one means 99%, 0.01. But I think it'll make more sense at the end. Just you're combining the idea about alpha with the null hypothesis in a way that's not correct. So hold off on that until we get through this problem and see if it makes a different sense to you. Okay. So the alternate hypothesis, we don't know whether his diet is better or worse. He has an idea, but he's not sure. So it'll say the sample rats, let's just say they'll be different than the pop, because we're going to run out of time if we do it any other way. Pop's the number of errors. Maybe they'll make more. Maybe he's breeding geniuses. Who knows? The next step is to compute T and get T computed. So T is equal to the sample mean minus the population mean. Put that over S divided by the square root of N. Here's our data. The population mean is 28. We already had that. Once he's made his hypotheses and he's ready to go, then he does a research project, and he tests his rats on how many errors it takes them to learn this complicated maze. He uses 25 rats, so N equals 25. It took them, I'm looking for it, hang on. Their mean was 29.5. It's not exactly 28, but it's not that far off. And the t-test is going to tell us whether it's far enough off that we can say that they're different. Okay, so their standard deviation was 3.57. Next, we're going to find T critical. No, we haven't solved for T computed, so sorry. So it's equal to 29.5 minus 28. Put that over 3.57 divided by the square root of 25. You can worry about whether or not you can do the math part correctly. It's more the logic part I'm concerned about today for you, especially. So just so you know, in the end, whoa. In the end, that comes out to be T comp equals 2.11. And I'm going to highlight it because I know we're going to need it highlighted for later. Okay. Next step, find T critical from the table. Jesus. My notes are all, this tablet and I today seem to be in a war. T critical from the table. We need to know alpha, which we already said at 0.01. We need to know whether it's one or two-tailed. We find that out by going back and seeing what we hypothesized in our step 3. And we said maybe his personal formula for rat food is better than Purina rat chow. Maybe not. He thinks maybe not, but he's not sure. So he went with a two-tailed hypothesis. Can you see that from what you put in there for step 3? One way that you can tell that that's what you did is when you look at the language in your alternate hypothesis. We just said they'll be different. We didn't say they'll make more errors. We didn't say they'll make less errors. We said they'll be different. In other words, more or less would be a problem for us. That's a two-tailed test. And we need to know degrees of freedom. Degrees of freedom is n-1 as per usual. And there were 25 in the sample. So degrees of freedom equals 24. I'm not making you do the hard math. I saved those for me. 25 minus 1, hardest thing today. No. Okay, now we need to find T critical in the table. So we're going to do just what Elijah said to do. You choose one tail or two tails. You're going to look in the two-tailed row. And you go across until you see 0.01. Remember, we set it at 0.01. We want to be 99% sure before we mess around with their food. Okay, that's the third from the right. Two tails, 0.01. And we go down to find 24 degrees of freedom. I picked this table because it has the blue and the white, so it makes it a little bit easier to find where you are. Somebody tell me what you get for T critical.
2.797.
Yes, you are the master. You're in charge of tutoring on how to use T critical. 2.797. Anybody want some help knowing how to do that? How to find that? Last chance. No. Okay. Now our next step will be to compare T computed and T critical. Green versus yellow. We're going to make a decision and then we're going to write a sentence. So 6. Make a decision. And the statement. In this class, you could do all the math right, but if you don't understand what your findings mean, you lose half of the points for the problem. You have to understand what you've done. Otherwise, there's no point in doing it. This is to solve research questions. If you go through running it all through the math and then you don't know what your results mean, then you might as well not have wasted your time. Okay, so we're going to make a decision. So to make our decision, we're going to compare T computed to T critical, and we're going to use, good God, it's way back here, right? I'm getting there. Here we go. We're going to use, can you see it now? It won't stay up there. I'll hold it. Can you see? Can you see that?
Even when you don't hold it, I can see the bottom of it now.
Okay, so if T computed is greater than T critical, then we're going to reject the null hypothesis. If T computed is less than T critical, we're going to retain the null hypothesis. Let's go back and look at our numbers. T computed is 2.11, T critical is 2.797. Which is greater?
The T critical.
Right, so we're going to say retain the null hypothesis. If T computed is less than T critical, we're going to retain the null hypothesis. So we're going to say retain the null hypothesis. But you have to understand what that means. That's why you're putting it in a sentence that sixth graders could understand, minus a little part in parentheses. Okay, so here's our sentence. Rats who ate the researcher's chow were not, there's many ways to write this, but I'm trying to write it in a way that makes it really clear to you. Significantly different than rats who ate Purina rat chow, population, in number of errors made. You could get fancier and you could say when running a maze, and you could readjust. You can definitely write this sentence more with different words, but I'm trying to put it in a way that's pretty formulaic. Okay, and then in parentheses, this is the part that most people lose the points on in these statements. T with 24, because there were 25 of them, degrees of freedom. This is T computed is 2.11. Now we are not going to write P is less than 0.05 because that is alpha error, right? Alpha was 0.01. Remember that table, reality versus the decision about the null hypothesis? Do you remember that table that we did? Where alpha is the mistake you make when you reject the null hypothesis, but it was true. Remember that kind of thing? That's what alpha means. Alpha error means that's how likely it is that you'll be wrong when you reject the null hypothesis, that there will not be a significant difference, but you mistakenly say there is. And by mistakenly, I just mean the math worked out that way. So we don't say P is less than 0.01 because we aren't 99% sure that there's a difference. We're not rejecting the null hypothesis at all. We're retaining the null hypothesis. That was the first part in this step. So instead of saying P is less than 0.01, we say N dot S dot for not significant. The results, the two groups, the population and the sample, are not significantly different. So if we reject HO, then we're going to write in a sentence, P is less than 0.05 or P is less than 0.01, whichever one we're doing with alpha. If we retain the null hypothesis, that's the one that says there's no difference. And that's what happened this time. We put n dot s dot, or small n, small s, either way, meaning not significantly different. Means not significantly different. I only have 2 minutes left in class. I'm not going to do more examples now, but you need more examples before you take a quiz on this. You need to practice. I'm going to set you up with the practice problems, and that's what you're going to do on Friday. You're going to spend time practicing. Okay? And then I will post on Monday, we're going to hold class, but I will also post the quiz on Monday